According to some climatologists, within a lifetime, we might be living in the next ice age.
That was the message in 1978. Notice he said, scientists tell us, climatologists predict. We're going to be going through some of that this morning. This is going to be a two-part presentation. Part one, we're going to do climate theology, history, CO2 science, climate science. Part two, that's going to be the fun part, the controversy. Climate economics, energy, transportation, and summary. You might be wondering, my background is in engineering. You might be wondering, what does an engineer know about climate science? I'm not a climatologist by profession. Well, in college, I did have thermodynamics, fluid dynamics, heat transfer, and one of my senior level engineering electives was appropriate technology, because even back then I was interested in environmentalism and concern for others and such. And so for my semester project and term paper, I designed a greenhouse. It was a specialized greenhouse. It was technically a thermal solar water desalinator. It was intended to use the sun's energy and the greenhouse effect to warm up water and evaporate it and then condense it so that you could distill seawater and use it for humans, animals, plants, whatever. So the greenhouse concept is not new to me. That was a long time ago. Also, I've spent about 19 years working on things like X-ray optics, visible light optics, temperature control systems with custom sensors and heaters for X-ray detectors on a CT system. And that can vary tremendous different operating conditions. It can sit in a cold room all night, and then they fire up the X-ray tube, which is 48 kilowatts, which, to put that in terms you might relate to, that's if you get a portable heater for your house, portable electric heater, the most those can be is 1.5 kilowatts. So that would be like 32 of those things going off simultaneously. That's a lot of heat inside that gantry donut of a CT. So a lot of temperature change going on there. And about a decade ago, I got seriously interested in climate science because I was really concerned about what the truth was. And so I have spent well over 1,000 hours of independent study looking into this. And if you still think engineer can't talk about climate science, I would ask you, well, what about this guy? You might recognize Bill Nye, the science guy. And if you notice, first of all, underneath here is context. This is a YouTube screen grab. So underneath, for YouTube, underneath anything having to do with climate change, you will be directed to United Nations website on climate change. We'll get into that in part two. But he speaks about climate on behalf of National Geographic and the Environmental Defense Fund. And his technical qualifications are, he has a bachelor's of science in mechanical engineering, just like me. And I doubt he designed a greenhouse in college or worked on temperature control systems for sensitive medical electronics. So, and I went to a better school too. Okay, climate change, is it catastrophic, in other words, relating to a momentous tragic event, or copacetic, very satisfactory? I'll let you decide that. For the video viewers who might be seeing this in the future, before you jump to conclusions, I would urge you to look at the whole presentation, parts 1 and parts 2, so that you understand the context of everything. And for the live audience, we will have a Q&A at the end. I may be asking for a show of hands on occasion. Okay, section 1, Christian perspective. First of all, we have to get the right mindset. Don't conform to the world, but be transformed by the renewing of your mind. Then you can test things. God made the glory for humans to use and steward and show his glory. He said, be fruitful, fill the earth and subdue it. That doesn't mean trash it, it means take care of it, because God took the man and put him in the Garden of Eden to work it and take care of it. The earth is the Lord's, and so we're stewards of his property. Some other references in the Bible about climate and blessings and taking care of things. God blessed the latter part of Job's life more than the first. 14,000 sheep, 6,000 camels, 1,000 yoke of oxen, and 1,000 donkeys, all producing methane at the same time. When the Israelites left Egypt and came into the promised land, God said, I'm going to bring you into a place with water. Notice streams, pools of water, and springs. If you've ever been to the Mideast, you know water is very critical. So first and foremost, he says, yes, there's water there. You won't get dehydrated. And then he talks about crops. And then, interestingly enough, he says, a land where the rocks are iron and you can dig copper out of the hills. That sure sounds like a mining permit to me. So God is not opposed to human beings using the earth's resources for their benefit. Now, keep in mind, back then they weren't doing strip mining and leaving toxic pools of chemicals behind. But as far as using the earth, it is for our purpose. He doesn't want us to waste it. And then the reference in Revelation there on Judgment Day, destroying those who destroy the earth. Primarily that's in a spiritual context, because when Adam sinned, the ground was cursed because of it. And you go to Romans and it says the universe is in decay because it's in bondage to sin. But that, there's definitely, God throughout the Bible talks about good stewardship. Now, there's differences. This is a really controversial thing, because some people have a very different philosophy, but the Bible says God did not create the earth to be empty, but formed it to be inhabited. Humans are not parasites. We're the reason that the earth exists. God gave us this as our home. And it is our current home, but not our permanent one, because in the end, they will perish, they will wear out like a garment, like a clothing, you will change them, they will be discarded, but you will remain the same, and the children of your servants will live in your presence. They will be established before you. So heaven is our permanent home, not this one. So how should we treat the earth? Use it. God gave it to us to use. Appreciate it as a gift of God. Take care of it because he told us to, but don't worship it. Let's go through a little climate history. Start out with creation. Everything's awesome. And the climate was so nice, Adam and Eve didn't even need clothes. That's how nice the climate was. Think about that in a Wisconsin winter. Okay? Next, Adam and Eve screwed it up, of course, as we know. And we don't know what, if any, changes to the climate there were. The Bible doesn't seem to be totally clear on whether there was rain before the flood or not. There's differing opinions on that. I don't know. And then we have catastrophe. The big blue marble was all blue at that point, no land. I did omit the clouds because that was too hard to draw them in. And Noah's Ark is way too small to see on that scale. After the Ark, because of all the most likely continental drift, volcanic activity and such, we had a cold spell there for a while, and then that ended and we are in our current climate. When Noah exited the ark, God gave him a pledge. He says, as long as the earth endures seed time and harvest, so you're going to have food, cold and heat, summer and winter, day and night will never cease, and if you look in Job 38, that's when Job and his friends have been going on for about 36 of those chapters, talking back and forth, and finally God shows up and says, where were you when I did all this stuff? When I made these storehouses of this and that and told the sea where its bounds were and such. We have to admit that we don't know everything either. There's a lot of stuff humans are not going to figure out this side of heaven. Note that God said that after the flood and sealed his promise with a rainbow. So when you see a rainbow out there, think of climate change. There are going to be variations in the climate, as we saw previously. We'll get into that a little more, but always around a habitable mean. 4 questions. Has the average global temperature risen over the past century? We'll try to answer these too. Is temperature rise unprecedented? Do glaciers still cover the poles to the mid-latitudes? And the MWP stands for medieval warm period. Is the temperature rise likely to become catastrophic? And how much of that is due to anthropogenic, meaning human-caused stuff? And we'll get into that in section 4 and then in part 2. So here's a little bit of climate history. We did not have high-precision thermometers going back thousands of years. We've only had that for maybe 150 years. So this information is anecdotal, and we reconstruct history based on that. But there is a frozen Tiber River that goes through Rome. So imagine frozen Rome, and snow remaining on the ground for lengthy periods. Then you had the Roman warming period, grapes and olives growing further north than possible in previous centuries. Then you had the Dark Ages. That was a pretty bad time. Tree rings show some problems with growth, and the Black Sea froze and the Nile froze. Can you imagine the Nile River freezing today? The Nile, that's in Egypt. That's hot. And the Black Sea doesn't freeze today. Doesn't come close. Medieval warming. That's when Greenland got its name. Norse colonized it and were there for about 500 years before the climate change drove them off. And grapes grew throughout Northwest Europe in areas where grapes can no longer survive. And life was good then. Little Ice Age. Life was not as good. There was some cold periods there. Thames River froze regularly, with the last ice festival in 1813. The Thames River is the one that flows through London. That does not freeze nowadays. So we know things have been warmer and colder in the past repeatedly, even though we don't know exactly how warm and cold it was, but we do know things changed. But all of these were around a habitable mean. Modern warm period. Most of the current warming, we'll see this on some graphs shortly, occurred prior to 1940, and then we had cooling from 40 to 75. That's what Mr. Spock was talking about earlier. For those of you who didn't recognize that, that was Leonard Nimoy. He played Mr. Spock in the original Star Trek series, which, if you think Star Wars was long ago in a galaxy far away, that was longer ago and further away. So global warming alarmists, and then things have been warming up since 1975. And now scientists are worried about the warming instead of the cooling, and how much of that is due to mankind. Okay, so this goes from roughly the year 0 to 2000, and as I said before, prior to that last little section, we don't know these temperatures for sure. There's been a number of attempts to reconstruct this using ice cores, tree rings, and things like that. So we might be able to get like a general idea, and we can put that together with the anecdotal information about rivers freezing and grapes growing and things like that. So, this is kind of uncertain. It's, some estimates and guesswork. This is not. This is in the modern precision thermometer era. This was part of a scientific paper. Notice the title of it, Climate Change Chilling Possibilities, 1975. That's NAS, National Academy of Sciences. That's where this graph came from. Notice I said it's undoctored. It's hard to find unadjusted temperature history in the US now because it's not, there's a different attitude toward history now than there was before. I'll just leave it at that. These kinds of, I mean, this is actual historical temperature, and you can see late 30s. Remember the Grapes of Wrath, the Dust Bowl, the 30s? That was a hot decade. We know it was a hot decade, okay? Then you have this period of cooling for 30 years, and then Leonard Nimoy got excited and told us that scientists and climatologists thought it was going to keep going. And then this is now the most modern era. This is the satellite era. Starting right at the end of '78, we finally got some satellites up that can circle the whole Earth and get a pretty good picture of global temperatures. Because this, now keep in mind, this is mostly an estimate. That last part is thermometers, but even in the thermometer era, if you're trying to look at global temperatures, the thermometers were not distributed around the globe. There are very few thermometers in Siberia, Africa, South America, etc. They were mostly in the US and Europe. So we don't have real good global records, even in the more modern era. But for context, okay, you can see, there's been some ups and downs, okay, and then in the 20th century, there were some ups and downs, and right about the end of this graph, with just a little bit of a gap, is where this thing starts. And this thing is going up, and I have high confidence in the accuracy of this. It took them probably about a decade to tweak everything and get all the calibrations correct, because initially it looked like things were going differently than they thought they should be, and so they went back and checked their numbers and recalibrated, because I'm not going to go into the details, but satellite temperature measurement is really complicated. And so what this is showing is an increase of 0.4 degrees C per decade after the temperatures dropped for 3 decades. And I believe this is real and accurate, and especially because I'm familiar with the two guys. The UAH stands for University of Alabama at Huntsville. There's two guys, John Christie and Roy Spencer, were the guys who kind of figured out how to make this work. And both of those are very upstanding scientists. This slide I'm going to take some time on, because this is perhaps the most important slide in the entire presentation. If you understand this slide, you are going to be ahead of 99.99% of the planet's population. I first discovered the information on that slide in this book, Unsettled by Stephen Koonin. Stephen Koonin is former Undersecretary for Science, U.S. Department of Energy in the Obama administration. He has a PhD in physics, taught physics at Caltech. He's been on the boards of a whole bunch of different national labs and such. This guy is Mr. Resume, okay? So I first saw a variation of this in his book and then went searching for it. Could not find it on any government website, found it on a third-party website. Interesting, because that came out originally on a government document. So what is this? Oh, before I forget, this was actually 2 graphs. The red graph I just put up there the way it was. The blue graph I just turned it upside down. Using PowerPoint, you can say flip the picture upside down, and then that way I could tuck it up under the red graph, and then you can see from 1895 to about 2020, you can look, and for every single year you can see the high temperature record, the low temperature record, and line up all the years to see trends. Now, this is not showing actual temperatures, just so you understand. I need to explain this, but this explanation is really important. What this is John Christie had access to all the weather stations in the US. And so he went and he said, okay, how many of those have good records going back to about 1895? There's a roughly 800. I'm going to round it off to 1,000 for explanation. So for every weather station, it's keeping records of temperatures all day, every year. And for every day of the year, that weather station will have an all-time record high for that date in history and an all-time record low. And this is a chart of absolute record highs and absolute record lows. So let's say you have a weather station and you set a high record in 1930, and then you set another one in 45 and another one in 1970. Well, you erase the earlier ones and just keep the one from 1970. It's like a deck of cards, you know. If you have the ace of spades, nobody else has it. So there's only one data point for the high temperature record on a given date for a given weather station. So if you have 1,000 weather stations and 365 days in the year, that means there's going to be 365,000 data points on top for the high temperature record for the day of the year, and then 365 low temperature records. And then what you do for each calendar year, you say, okay, for 1940, how many weather stations recorded record highs in that year? And how many recorded record lows in that year? And you put all those together. And if the climate is not changing, let's say you live in an area where, you know, it's this, if we had absolutely stable climate, just minor variations year to year. So the odds of any particular year having the high temperature record or the low temperature record would be the same as for any other year. So in statistics, we would call this a flat distribution. So what you should see, if nothing's changing, is across the top, you see little wiggles up and down, minor variations from year to year, but no particular increasing, decreasing trend. Same thing on the low side. So you can use this to discover whether there's trends in the data or not. So if you see, let's say, for example, in 1895, you had a lot of high temperatures that, let's pick a later year. Let's say 1910 was a really, really hot year. Okay, you'd set a lot of records for that year, and then maybe 1970 was a really cold year. You set very few high temperature records for that year, and vice versa. So that if 1910 was hot, 1911 is hot, 1912 is hot, you'd see big high spikes like this, okay? Because that would indicate that those years were hot years. I don't know if I'm explaining this clearly or not. So just by a show of hands, how many of you think you understand what I'm talking about? How many don't? Okay.
What are the numbers on the left-hand side?
Okay. This is the number of records. Okay. So all it's doing is, think of this like rolling a die. You have an equal chance of rolling 1, 2, 3, 4, 5, or 6. So if you rolled a die 1,000 times, you would expect to see similar numbers for 1, 2, 3, 4, 5, and 6, right? If it was a loaded die, then it's like, oh, hey, how come 5 keeps coming up? Okay, So this is just recording the statistics. How many high temperature records got set in a given year? How many low temperature records got set in a given year? If you had a really hot summer, you might say, whoa, yeah, or a really warm winter, you could set a lot of high temperature records too, or vice versa. So if you have any more questions individually, bring it up in the Q&A. We can go into more detail or afterwards. I think most of you are getting it. So what the chart here showed a warming trend up to the 1930s and then cooling into the 70s. And then warming slightly again after that. So if you look here, you see more high temperature records getting set in the 30s, but same kind of fair number of low temperature records, less of them in the 30s, more high temperature records. And then what do you see from the 30s to the 70s? The number of high temperature records drops a lot. You see some white space here, right? Very few high temperature records getting set in the 70s. Leonard Nimoy was getting very worried, and the scientists, who said, hey, things are cooling off. We are setting that. So the average temperature, keep in mind, is going to be, if this is the high and whatever is the low down here, the average is halfway in between. So if the lows are staying about the same and the highs are decreasing, right? So you got the highs coming down, lows staying the same, average is halfway in between. Let's just say, for sake of discussion, the average is halfway in between. So the average temperature is going to be coming down, even if the low temperatures are not changing, because the average is going to be in between the highs and the lows. And then, here's the interesting part for modern times, okay? High temperatures are staying the same since the late 70s. We're not seeing an increase of high temperature records here. That's a pretty flat distribution. And if you look at the numbers here and the numbers here, you can go back 125 years and you're seeing similar numbers here to there. What that tells you is the Earth is not getting hotter. The summers, we're not frying. We're not getting excess heat waves. What's happening is our low temperatures used to be down here. We're getting fewer low temperature records. So our high temperature records are staying about the same. Our low temperatures are increasing. So your average is increasing. So if you go back to here, okay, you see the average temperature is decreasing. Go here, you see the average temperature is increasing. So what this chart tells us is we're not getting hotter, we're getting less cold. Remember Adam and Eve back in the garden? Life was good, the climate was mild. Our climate is becoming milder. That's what this chart is telling us. Our climate is becoming milder. So you have to look beyond the averages. We're not getting higher temperatures, we're getting less low temperatures. That means generally longer growing seasons. The people who like to go to Florida in the winter maybe don't have to go as often. Snowbirds. And, we're getting close, the phrase comes to mind from the Crosby, Stills, Nash & Young song, Woodstock. We got to get back to the garden. I think they were referring to the Garden of Eden, but they also talked about a billion-year-old carbon, so don't get your theology from them. So the average temperature is increasing slightly. But again, you have to keep that in context as well. So if the average temperature is increasing slightly, this is Oregon. This is a little milder than southeast Wisconsin, but that's the yearly temperature range for Oregon. There's it for the planet. I put in some numbers for Waukesha, okay? Our extreme temperature variation is about 77 degrees, so we'd be about there for extremes. For average, if you took the average temperature in January versus average temperature in July, it would be a little milder. But so if we increase a degree over a century, you know, how consequential is that? If winter, let's say, the other thing is, where we're not setting the low temperatures nowadays is typically at night and in winter as much. So we're getting, again, back to the garden, or closer, maybe just a teensy-weensy bit closer to the garden in our climate. And there's negative things about that. If you're an ice fisherman or a snow skier, your season might be shortened by a day or two. But, you know, on the bright side, you might have fewer people freezing to death and things like that. So, since the flood, for humans, remember God made that promise to humans. And the other thing is, to remember is, during the post-flood ice age, humans were not all over the planet then, because it took them a few hundred years to get some decent population and spread out over the continents. The ice age happened in the few hundred years after the ice age, and humans would have taken probably many hundreds of years. Think about the spread of the gospel, how long it's taken to get that around the world. And back then, there was zero infrastructure. The disciples at least had Roman roads and ships and stuff like that. So if people are just migrating on foot and they're not running away from some immediate danger, you know, how fast are they going to migrate? It's going to take them hundreds and hundreds and hundreds of years to disperse over thousands and thousands and thousands and thousands of miles. So from about 40 to mid-70s, temperatures cooled while CO2 increased. That's another anomaly. They never explained to us why that happens. And then for the last few decades, high temperatures have not increased, but the low temperatures have been getting mild, raising the average. And I believe it is going up. As we've seen before, climate has gone up, climate has gone down before humans had a chance to influence it. We'll get into the carbon dioxide greenhouse effect, which is real. But first, let's get into the CO2 science. Just to note in passing, the Inflation Reduction Act, which most of you have heard of 2022, amends the Clean Air Act to designate CO2 as a pollutant. So that is now officially, by law, a pollutant, according to the government. Here's what the Bible says about that. And to all this is Genesis 1, so this is very beginning. To all the beasts of the earth, all the birds of the air, all the creatures that move underground, everything that has a breath of life in it, that includes humans, I give every green plant for food, and it was so. God saw all that he had made, and it was very good. This was before sin, right? So humans were eating plants back then. And it's interesting because if you look at this is the chemical equation for photosynthesis, okay? Humans, when we breathe, and animals too, you know, God was addressing the animals. He said all the animals and humans eat green plants for food. When humans eat green plants for food, when we breathe in and out, we are breathing out CO2. We breathe in oxygen, we breathe out CO2. And we also breathe out water vapor. On a cold winter morning, you can see your breath. Why is that? Because there's water vapor in your breath. So we are breathing out constantly CO2 and H2O. by God's design, that goes into the atmosphere and the sun shines. And then every plant with chlorophyll in it, every green plant takes those inputs. This is plant sugar, and this is oxygen. So what we get rid of, plants use and give us in return oxygen. And this plant sugar is also a human and animal nutrient, but it's what the plants use to build themselves. That's why grass grows, that's why trees grow, that's why fruit happens, potatoes, peanuts, everything, bananas, is dependent on that. So our food comes from our waste. And the plant's products are used for our food. Not only that, but if you go to a dairy farm, they have things called manure spreaders. Cows poop. So do humans, and we use that human poop for Milorganite. Now you know what's in it. But for disease reasons, we don't use Milorganite on food products. We put it on golf courses and lawns and things like that. But every dairy farm, or at least the ones I'm familiar with, have a manure spreader. When they clean out the barn, they put it in manure spreader, throw it back on the field. Why? Because there's nitrogen and other nutrients in the poop, and that's what helps plants grow. Our waste makes plants grow. Plants make us grow. What a genius God was. I mean, what an amazing thing. He designed that from the beginning. Here's a picture of the carbon cycle. So on land, you have plants growing and being used and decomposing and stuff, and some of the stuff goes into the soil and decomposes. These numbers are gigatons. Okay, all these numbers here. Okay, this is large numbers of stuff. So in the atmosphere, there's about 730 gigatons of carbon, and the human contribution to that is about 3.5 gigatons a year, and we produce actually about twice that. So about half of what we produce goes into the atmosphere. The other half goes into the ocean and into the soil. So there's only that much. That's the guesstimate. I mean, these numbers always change, but that's the guesstimate there. I don't know that we're going to be able to get that all out, but I'm not going to try to go through and explain all this, but God set this all up a long time ago when he created the stars and the planets and the earth and made the earth our home. And God knew what he was doing. CO2 is good for plants and humans. I'm not going to go through that. That's an eye chart, but it says on the top, 55 benefits of atmospheric CO2 and enrichment. And these are all the different benefits that plants get out of CO2. So I guess I would, if you're a biologist and you're growing plants and doing research on them, is CO2 a pollutant or is it plant food? These are all benefits. If you're operating a commercial greenhouse, not the kind like at Stein's Garden Center where they just park the plants in there momentarily to shelter them while they're being sold, but I mean actually growing plants in a greenhouse. The atmospheric concentration of CO2 is about 400 parts per million. Greenhouses typically run somewhere, if they have the money, depending on the economics, but they like to run about 2.5 times that, around 1,000 parts per million in a greenhouse. Why? Because 55 benefits of CO2 makes plants grow faster, stronger, healthier, more disease resistant, more drought resistant, et cetera, et cetera, et cetera, et cetera. Plants love CO2. It is plant food. And there's some evidence of that. There's a extinct volcano called Mauna Loa in Hawaii, on top of which is the place in the world where we measure carbon dioxide. It's a good location because it's on the ocean and it's away from industry and stuff like that. And so that's been going up for as long as they've been keeping records, which you would expect because we're adding carbon dioxide to the atmosphere. But so is wheat production going up. That's 1960 to 2016. So is corn. There's an increase in area, but there's even more of an increase in yield. So our land is becoming more productive. There's a number of reasons for that. Some of it is better farming techniques, better seeds, etc. But a good portion of that is also CO2. You can find this article on the nasa.gov website. So this is not some conspiracy theory here. It's an article about a major international study, 32 authors, 24 institutions, 8 countries. This was a humongous effort involving many people and institutions. And they looked at 35 years of data. They were using satellite data to look, and the satellites can look and see how green things are by looking at different light spectra and things like that. And they found out 11% increase in vegetation in places that had vegetation. And then they said, well, okay, we've seen an increase in vegetation. What's the cause? 70% from atmospheric CO2 increase. So there's some evidence that CO2 really is plant food. But the even more surprising thing is, everybody says climate change is going to lead to starvation. What is that right there? Climate change, 8%. Increase of vegetation due to climate change. Increase, not decrease. Carbon dioxide, milder weather, crops like that. Who would have thought? Fossil fuels were apparently created in the flood. This is from the EPA.gov website. And this is telling us what we already know. It says much of the petroleum and natural gas was created in the Earth's crust at the site of ancient seas by the decay of sea life. As a result, these shale petroleum and gas deposits often occur in aquifers containing salt water, and they do. Most petroleum wells have salt water in the bottom, in sedimentary rock with dead sea life in there. I wonder how that could have come about. Perhaps a worldwide flood? Maybe. So that raises some questions. Okay, what are fossil fuels made of? Well, fossils, right? Where'd the fossils come from? Ancient life. How'd they get in the ground? Well, ancient seas, some flooding. Were there any fossil fuels in the ground on the 6th day when God saw that it was good? I don't think so, because death and decay did not come into the world until man sinned. So that says there's no fossils before sin. And if the carbon wasn't buried underground then, why is it so terrible if it isn't buried underground now? Remember, in the perfect world, that carbon was in the biosphere. That was growing the Garden of Eden. That was an ideal life. Now, you do have to be careful about things that can influence the climate. You don't want to be just about things that can influence the planet in any major way. You don't just want to be helter-skelter about things and trashing things and being unconcerned. But in 1 year, humongous amounts of carbon were taken out of the biosphere and buried for many thousands of years until people in the 1800, well, I guess coal goes back a little more than that, but until pretty much the modern age, when mankind discovered, hey, there's oil and coal and we can burn that stuff and really get some good benefit out of it. And if we put it back into the biosphere from which it came, how bad should that be, just from a logical standpoint? Isn't it interesting that the people who are most fanatical about future global climate catastrophe are the same ones who deny that it happened in the past with the Genesis flood, right? Oh, no, there was no Genesis flood. No, that's just a fairy tale. But there's a climate catastrophe coming just around the corner. You have to worry about that one that we project, but don't worry about the one that actually happened. If you realize the flood buried those huge amounts, you're less worried about that carbon resurfacing over a long period of time. And if we're all just evolutionary accidents, why does it matter if we get burned or frozen or whatever in the future? And when you see proposals to address these issues, ask yourself, who gets more power and or money from it? Who does it benefit for all these programs? Okay, I'm not going to answer that right now. That's politics. Those people who are denying that it happened in the past say nothing is designed. The Earth's climate is unstable. Humans are accidents. Humans are perfectible. We can create utopia on Earth, but they don't want a milder climate to help with that. We have to live for this life because that's all we have. There's no absolute moral standards, so if you need to lie to get ahead, go ahead. And the ends can justify the means. Just ask Stalin. Oh, that's politics. Okay, understanding climate science. Remember, science is always tentative truth. God's word is absolute truth, always true. Heavens declare the glory of God. It's the glory of God to conceal a matter, to search out a matter. It's the glory of kings and scientists. Sanctify them by the truth. Your word is truth, not necessarily our concept of truth. I'm not going to go through all of these. GHGs, greenhouse gases, weather is what happens day to day. Climate is what happens over generally about a period of 30 years, they say is, you look at that window and say, okay, whatever happens in a 30-year period, that's the climate. But that's not hard and fast. That's just kind of a general guideline. Climate change, global warming, anthropogenic, again, human-caused. Catastrophic is the big question, and we'll look at that later. Crash course in heat transfer. I'm not going to go through this. I'll just put the slides up for the benefit of the video geeks. There are 3 modes of heat transfer. We're going to be primarily concerned with radiation. Definitions, albedo might come up. That's how good of a mirror things are. Emissivity, how good of a piece of charcoal you are. Photon is a quantum of radiation. On this chart, 2 things I want to highlight. This indicates temperature, absolute temperature, kelvins. To relate kelvins to degrees C, kelvins is about equivalent to 0 on the 0. Kelvin is a 0 scale, so it starts out at absolute 0, which would be, is it 459 F? It's about 273 degree minus 273 C, and I think it's 459 F. I might be wrong with that. But the point with this is the sun has a temperature of a little over 5,000 kelvins, and at that temperature, its peak emissions are in visible light. Okay, it emits less energy in the infrared, less energy in ultraviolet. This doesn't go further, but you get ultraviolet, X-ray, and then gamma. So that stuff's really nasty. We don't want anything to do with that. And UV can give you sunburn and skin cancer, so we don't want much of that either. But the interesting thing is God designed the sun to be visible to the human eye, which he also designed. So where we can see is where the sun is, and vice versa. So maybe there's some design thought that went into that. The other thing I want to point out is the amount of energy that you dissipate is dependent on temperature to the 4th power. This temperature on the Kelvin scale. So just a tiny change in temperature can have a humongous difference in emitted energy, and that we'll see in a second. Okay, this is another complicated thing. This is illustrating the greenhouse effect. So there's a color code to this. The sunlight is shown as yellow. The Earth absorbs some of the sunlight and gets warmed up from the sunlight. And then the Earth emits energy, but it emits it in the infrared spectrum. If you're familiar with like a thermal camera, sometimes they do energy audits on houses, and you can see what, where's the energy, where's the heat coming out of my house, or like the military uses thermal sights on a lot of their weapon systems so they can see in the dark, they can see hot and cold, and I should have probably made a thermal image. Oh well. Anyway, so you have sunlight coming in, some of it gets reflected off of clouds, some of it gets reflected off the Earth's surface, and then the Earth absorbs some of that, and because every body like the Earth is a body, emits radiation depending on its temperature. The Earth's temperature is about 300 Kelvin. So it emits in the infrared spectrum. You can see it in heat if you have a thermal camera. And so that's a much longer wavelength, lower energy. And there's about 4 common greenhouse gases. Water vapor is the predominant one. Carbon dioxide is one, methane, and nitrous oxide are the big 4. And what happens is when humans burn fossil fuel and do other activities that put CO2 and methane in the atmosphere, you get a greater concentration of molecules that they work like a greenhouse. Greenhouse glass allows sunlight to come in, but the characteristic of the glass is such that when infrared waves, which are longer waves, try to go out through the glass is largely opaque to those rays. And so the glass absorbs it and doesn't let it through, and the glass warms up and the greenhouse warms up, and that's how you get the greenhouse effect. In the atmosphere, it's a little more complicated than that because it's a 3-dimensional moving model with astronomical numbers of moving parts. So what this is trying to show is, okay, this is without burning, what they're trying to portray here is this is without burning fossil fuels, this is with burning fossil fuels. So what you have is the red is the infrared, that's why it's red, okay, and then the carbon dioxide molecules, they just show a few of them because it'd be too busy otherwise, but carbon dioxide molecules absorb that. They let through sunlight, but when the infrared tries to go out, the carbon dioxide blocks it largely. And water vapor blocks it as well as those other ones. And so I'm going to go to what this is showing is the greenhouse gases are absorbing the infrared. They're not allowing it to pass. They absorb it, and then they re-radiate it in all directions, and a lot of that gets radiated back down to Earth. And what it does is it kind of sets up an obstacle course for infrared to get back out to space. And why does it need to get back out to space is because of the next slide. If this works, there we go. Okay, Earth's energy budget. Okay, so these actually have numbers. This is watts per meter squared. And if you have a closet and you buy shoes and you keep putting shoes in the closet fills up with shoes. So if you want the closet to keep the same amount of shoes, you have to throw out some shoes. Or if you're throwing out shoes and you don't buy any shoes, your closet gets empty. Same thing with heat energy. If Earth is the closet and light is the shoes, you have to balance whatever's coming in with whatever's going out. Because if more energy comes in than goes out, the Earth gets full of energy, and that means heat. That means global warming. So some sunlight gets reflected off clouds, some gets reflected off the Earth's surface, most gets absorbed and then emitted as infrared and goes up into this obstacle course called the atmosphere, and has to work its way through. And eventually, it works its way through, but the more difficult it is, the more lengthy the obstacle course, the more difficulty it has getting through. And some of that stuff will actually warm up the atmosphere by being absorbed and re-radiated umpteen gazillion times. And so you can get some warming if that obstacle course gets a little longer. And that's that's the effect that more carbon dioxide has as far as a greenhouse. It may down where we are on the surface, the effect is saturated. So if you imagine a video game with just a flat surface and just random trees widely spaced, and like you do what is it, Grand Theft Auto or whatever, you're chasing cars through streets and crashing and then regenerate, as soon as you crash you hit the reset button and you keep on going. Infrared and carbon dioxide and water are kind of like that. So think of an ATV just going across a flat surface with random trees around. Eventually it's going to crash into a tree, and then the tree being a molecule, it'll re-radiate it, and that's like hitting the reset button, and the ATV goes zooming off in some other direction. So down by us, the trees are pretty dense. As it works its way up through the atmosphere, eventually the trees, because the atmosphere gets thinner, trees get further and further apart. Finally, at the top of the atmosphere, it's thin enough where the ATV goes through the trees and out into space. So if you have more carbon dioxide in the atmosphere, the carbon dioxide stays at a level where it can keep absorbing the infrared to a higher and higher altitude. It's kind of like in your attic, you say, I want my house warmer, so I'm going to put an extra layer of fiberglass in my attic. When you put more CO2 into the atmosphere, it's kind of like putting another layer of fiberglass in your attic. Now, I will state categorically, CO2 is a greenhouse gas. Greenhouse effect is real. It has some non-zero effect on Earth's temperature. The question is that effect 1%, 99%, or somewhere in between? That's the big question. My personal gut feeling from studying this and looking into this and knowing what I know and looking at history and stuff like that is it is most likely a minority contributor, because as we have seen in the past, climate has changed, and what we'll see going forward, we're going to see other influences on climate. And so climate changes even when carbon dioxide is not being generated by man. We've had upswings and downswings, and man wasn't putting huge amounts of carbon dioxide in during those times. So obviously other forces are at work. I just want to point out one other thing here. When it's warmer, water evaporates, goes into a cloud, and then the cloud rains. When you boil water on the stove, you have to put heat into it, right? It doesn't boil if it just sits there. You turn the flame on or turn the electric element on and warm up the water and cause it to boil. If you have a lid on, you notice you generally get condensation there. The water condenses there and the lid becomes pretty hot because it takes heat to evaporate water, but when water condenses, that same heat that it took to evaporate it comes back in and heats up whatever it's condensing on. So when you have that cold beverage and you see the condensation on it, that condensation is causing your beverage to warm up. And that's the principle behind heat pipes, which is, this is a picture of the Alaska pipeline. These brown things might look like innocent little things, but in actuality, they're heat pipes. You have a fluid in the bottom. What they're trying to do here is keep the permafrost frozen so the pipeline is stable. They don't want it sinking into the ground. These brown things are actually heat pipes, and these things are radiators to help cool the top end. So if the permafrost starts getting warm, it boils the fluid, condenses on the top, and the radiators help dissipate the heat. We have a heat pipe here, basically. When you evaporate water and it condenses, what that does is, it's kind of like in Monopoly, you get a card that says go to go and get $200. It's kind of a shortcut halfway through the obstacle course. So it helps to put heat into the clouds where it can radiate out better into space. So I would call that a negative feedback. We'll talk about what a negative feedback is, but God designed that in. He knew what he was doing. This is so far simplified. I mean, if you think it looks complicated, it's unimaginably complicated. And the climate models cannot model clouds, they cannot model the water cycle. We'll get into that later. But the two most complicated subjects that I have found in all of science, I've been studying science pretty much all my life. That's why I became an engineer. Two most complicated subjects that I've come across are climate and that thing, the human cell. We're nowhere close to understanding a human cell. If anybody tells you they understand it, okay, tell them to name every single protein and all of the functions of every single protein and all the other things that are zillions of things that are going on in the cell. We're nowhere close to understanding a cell. We're nowhere close to understanding climate. I talked about greenhouse gases. Okay, this is the incoming energy. That's the outgoing energy. This and that have to ultimately add up, or the Earth gets hotter or colder. What I wanted to do is just kind of give you, this is wavelength. So this is infrared over here. That's your visible light over there. And this shows you that water vapor blocks a lot of stuff. Carbon dioxide, this is called the atmospheric window here. Carbon dioxide basically pokes its head in the window and blocks part of the window. It says, "Hi there, remember me?" Okay. And another interesting thing, freebie here, Rayleigh scattering. This is due to nitrogen. This is up on the blue end of the spectrum. If you wonder why we have blue skies and red sunsets, it's the Rayleigh effect. What happens is sunlight comes in and the blue light gets scattered by nitrogen in an almost infinite hall of mirrors. And blue light has a hard time getting through. When the sun is bright overhead, the atmosphere is thin enough, blue light can get through it. And when it's sunset, if you think of a shell, if it's coming in straight through, there's this much thickness. If you're coming in sideways, there's a much bigger thickness. The blue light has a hard time making it sideways through the atmosphere, which is why you get red sunsets and sunrises. And because the nitrogen is an almost infinite hall of mirrors. It's scattering the blue light all over. So when you look up, you see a blue sky. If you're on the moon and you look up, you just see black. There's no atmosphere. So that's just part of God saying, I want to make life beautiful. I want to give you pretty sunsets and a pretty sky. Just part of God's engineering. Okay. Again, I'm not going to go into this. What this illustrates, this is the carbon dioxide sticking its head into the atmospheric window. This is a notch. And if you look at these two, they look pretty much identical. And I'm not going to go through this, but the difference between these is this is a doubling of carbon dioxide concentration. That's 300 ppm, 600 ppm. We're at about 400 right now, but we were close to 300 before. And so the difference, what this is a pictorial description of the obstacle course for the outgoing infrared radiation. And what this says is watts per meter going out here is about 300, and it's only about 297 there, about a 1% decrease. So that's what we're talking about, the temperature difference, with a doubling of carbon dioxide, which we're not close to yet. But the interesting thing is, a 3/4 of a degree K increase, or degrees C, whatever you like, for 600 parts per million gets you exactly to where you were here. So what this is saying, remember I said radiation is proportional to temperature to the 4th power. So just a slight change in Earth's temperature, this is a little over a degree F, if you want to relate to that. Okay, slightly over 1 degree F. What it does is it kind of gives Wheaties to the outgoing radiation and says it's brighter. And so a brighter light through a smaller window gets you the same amount of energy going through the window as a dimmer light going through a bigger window. So that's the trade-off. So if you hold everything else the same and Earth heats up about 1 degree Fahrenheit, it will emit enough energy to balance out a doubling of CO2. Now, it's a whole lot more complicated than that. There's a whole bunch of other moving parts, so I'm not going to get into that. I'm just saying that there are some compensating factors that God built into the universe. Again, I'm not going to get much into this. This is just designed to kind of show proportions. What I'm trying to illustrate here is the blue boxes illustrate the effect from water. The black boxes illustrate the effect of CO2. The green box illustrates the effect of methane and the nitrous oxides and the other miscellaneous stuff. So about 2/3 of the greenhouse effect is due to water, and about 1/3 of the greenhouse effect is due to carbon dioxide sticking its head in the window. Some other factors. We don't even know all the factors. Like I said, this is like a human cell. We're nowhere close to figuring it out yet, but I just want to touch on a few. Clouds. I'll go into that in a minute. Air pollution, particulates. When we get big volcanic eruptions, it actually cools the planet, and when we burn a lot of coal, that puts a lot of particulates into the planet. So part of the reason that a contributing factor to perhaps some of the cooling temperatures we saw from the 40s to the 70s may have been increased coal use, because you're putting more particulates up. Particulates in the upper atmosphere reflect sunlight out, and it cools the Earth just like a huge volcano. In the early 1800s, there was a year without a summer because I forget the name of the volcano, but it was, whether it's Krakatoa or whatever, I'm not sure if that was the one or not, but it put so much ash into the atmosphere that the summer was barely better than winter, and tens of thousands of people around the globe starved to death because they couldn't grow food. Okay, changes in the sun's output, changes in the moon's orbit, and many, many more. Okay, clouds. This is a fairly recent revelation, and we found out that we really do need to look at clouds from both sides now. I'm not going to sing that. You can play that at home. But it turns out if you get more clouds, that lower, thicker clouds cool us, and high, thin clouds warm us. The lower, thicker clouds, I think, dominate the scenario because most of the feedbacks I've looked at say that clouds are a net cooling factor. So if you get more water evaporation in a warmer world, you may get more clouds, which might cool you back down. This is a record of sunspots. Galileo may not have discovered sunspots. There's some dispute about who actually did, but Galileo studied them and documented them, and that was in the early 1600s. And then we had the Little Ice Age and with the Maunder and Dalton. This is the Maunder minimum and the Dalton minimum. The scientists looking up at the sun in this period here didn't see any sunspots. And they said, was Galileo drunk or what was going on there? Because he was talking about these sunspot thingies and we don't see any. And historically we figured out, oh, that was the Maunder minimum because there were no sunspots. They were looking for them, they just couldn't find them. Well, they've been looking for sunspots ever since, that's 1611 right there. Okay, 2001. And this happens to, sunspots are kind of counterintuitive. Sunspots are kind of like acne on the face of the sun, and you would think, oh, if there's dark spots on the sun, it should be cooler. But counterintuitively, the sun puts out more energy when there's more sunspots and less energy when there's less sunspots. So, interesting coincidence. You had a little ice age here when there were few sunspots. Now there's more sunspots, and we have warming. And right about this time, they noticed the sea level started rising, okay? Keep in mind, this was a little ice age, okay? There wasn't a whole lot of melting going on. The Thames River was freezing in winter. That's how cold it was. So the glaciers were not receding. Greenland and Antarctica weren't melting, and so oceans weren't rising, but now we have more sunspots and things are warming up, and so they're melting now. And someone else charted sunspot activity in the more recent past and said, hey, I've noticed this coincidence here. If I look at sunspot cycles and I look at temperature, they seem to line up pretty well, and they line up better with sunspots than they do with CO2. So, that there is evidence that temperatures and climate are dependent on more than just CO2. There's a lot, like I said, there's a lot going on and we don't understand a lot of it. And I would have never thought this one, but I found it just recently. Lunar influence, LOD stands for length of day. This is 1850 to 2020. And it turns out there's variations in the moon's orbit that have a very, very slight influence on the rotational speed of the Earth. The moon is responsible for tides, just so you know. Okay, so the Earth has a big, the moon has a big influence on the Earth. And without the moon, we wouldn't have tides, and we wouldn't have ocean mixing, and God put the moon there to mix the ocean, so we have fish and stuff and food, and there's just, the more you look into this, the more you see, oh, there must have been a designer behind all this. But anyway, somebody charted length of day variations based on lunar influence and temperatures, and there's kind of an opposite correlation there. And you might think, oh yeah, this is just some right-wing nut job putting this out, and there's no credence to this, but the UN Food and Agricultural Organization says that this affects commercial fishing harvests. There are certain species of fish that do better in warmer weather and some that do better in colder weather. And so they look at this chart and they say, hey, you know, there's some correlation there with fish. I wonder if the Food and Agricultural Organization ever talks to the IPCC. I don't know. I'm just going to touch on geoengineering. Back in the 70s, when they were concerned about a coming ice age, there was talk of, well, maybe we should sprinkle soot on the ice caps, polar ice caps, and melt them to warm up the Earth, because otherwise we're going to freeze to death. Remember in the Dark Ages and the Little Ice Age, they had trouble growing food. I mean, that was a legitimate concern back in the 70s. They thought, we're not going to grow food, we're going to starve. And so they were talking, that was geoengineering. And there are some things you can do. You can actually spread particulate matter from airplanes, or spread reflective film out on the ground and change how light gets reflected. There is an organization and a person claiming that aircraft are commercial aircraft, routinely disseminating particulates or other chemicals by means of jet contrails. If you ever flown in a commercial aircraft, or you've ever looked at airline finances, the old joke is, how do you become a millionaire in the airline industry? You start with 10 million. Commercial aviation operates on razor-thin margins. And airplanes are very sensitive to weight. And jet engines are very sensitive to contamination in the fuel and things like that. If you think that commercial aviation is going to be hauling around tanks of chemicals and running any of that through their engines or spraying it out, I'd be interested in the evidence for that. This person also claims that they don't claim to have any technical education. They say experience in the solar industry. That does, but no further description. So I don't know if that was a salesperson, an installer, an engineer, a janitor, a manager, I don't know what. And they talk about the intermittent jet contrails. Sometimes you see gaps in the contrails. And he says, well, they're turning the sprayers on and off. If you've ever driven down the road and encountered patchy fog, that explains intermittent jet contrails. Okay, or if you've ever been in an airplane and hit an air pocket, that explains intermittent contrails, because there's chunks of air that are warmer and cooler than other chunks of air. So you're driving along the highway and you see, oh yeah, I got out of that fog. Oh no, here's another patch of fog coming up. That's just like intermittent jet contrails, okay? They don't demonstrate any significant knowledge of thermodynamics. So don't put a lot of credence into that. And basically, that's the end of part one. We do have plans to put some of this information on our website in the future, but that'll take a little bit, so.